Okay, this is section 13.4 on compound interest. The objective today is to model the value of an investment that earns compound interest. I want to start first by explaining the difference between simple interest and compound interest, which are two terms that you probably heard before. Okay, here's the main difference. In simple interest, according to the definition here, is a type of interest earned only on the original investment and is not reinvested. What that means is this: simply, let's pick an example. Let's say you invest $1,000 on an account that earns simple interest. At the end of that year, you earned $50. Okay, and you keep your account open. When they start calculating the amount for the next year, they don't use 1,050 as the initial amount. They keep using the original 1,000 only. Okay, so that the next year you'll earn another $50, and the next year you'll earn another $50. So you'll keep earning the same amount every year because they're using the exact same initial amount to calculate it. In compound interest, on the other hand, they reinvest the money that you earned. So let's say the first year you invested 1,000, and by the end of the year you have 1,050. The next year they're going to use those 1,050 to calculate the new amount, which means that you're probably going to get more at the end because now you have a larger initial amount. And at the end of that year, whatever you have is what they use for the next year, and so on. So your initial amount keeps changing based on how much you made the previous year. Where again, in simple interest, the initial amount never changes. Whatever you put in initially, that's what your initial amount is going to be every single year. We're not going to focus on simple interest because it is a constant rate of change. Okay, so like in the example that I said, it's $1,000 and you make 50, the next year you're going to make another 50, and the next year you're going to make another 50 because you deposited it under the same rate, right? So you're still making the same amount because your initial amount is the same. That's a linear growth. That's a linear equation. What we want to focus on is on compound interest, which is an exponential equation. Whatever you earn is a new amount, so your new amount is changing. That's exponential growth. So there are three main ways to calculate compound interest, okay? And I have them all here, and I'll go through all three of them, and we're going to use all three of them. There's three formulas here today. There's interest that is compounded annually, and it's only compounded once per year. When we say compounded, that means calculated. That's what it really means. They calculate your interest once per year when it's annually, and then they'll calculate at the end of the next year and at the end of the next year. Only every single year. So whatever you're earning throughout that year, that's what they calculate at the end of the year. Whereas this one, interest compounded more than once a year, sometimes it'll say your interest is going to be compounded quarterly. That means 4 times per year. That means 4 times every year they'll calculate how much interest you have earned, and whatever that amount they get, that's the new initial amount. Okay, and then there's interest that is compounded continuously, that they just keep calculating the amount that you have made every single second of every single day to see how much you have at that moment. Okay, so it's changing constantly. We're going to use all three of them. These two are very similar, and this one is probably the easiest one to use because it has the natural base, which is E. These are the two that you really need to focus on. Well, this one as well. They're all important, but these are the two that are a little bit more complicated to understand. Although this one is very familiar to you guys. Look how familiar that looks. That's something that we have used before for any exponential growth, right? So this is really the new one, and this one's also new. But it looks a lot simpler. It's a lot easier to use. Okay, so let's start first with interest compounded annually. That means once per year. Every year they compound your interest. V here will stand for the value of the investment that you make. P is the principal, or how much you deposited, how much you started with, the amount that it was invested. And R is always the rate, the annual rate. T is always the time. Okay, we're going to be using that one a lot. This other one, I think I'll focus on once we get to an example like that one. Let's focus on this one right now, and let's use it in the very first example. So let's move down to number 1. So here I've written the equation for number 1. I know it's the compound interest compounded annually because when I read it, it says a person invests $3,500 in an account that earns 3% annual interest. Find when the value of the investment reaches 10,000. So right there where it says annual interest, that tells me that it's compounded annually, once per year. Sometimes it'll say annual interest followed by the words compounded semi-annually or compounded quarterly or something. Like in number 4. Look at number 4 real quick. 2% annual interest compounded quarterly. So that means that it's not once per year, it's 4 times per year. Every quarter they compound it. Okay. This one doesn't say anything about that, so we know it's once per year. So we use this, the simplest of the formulas. Okay. So in this case, what I'm going to do first is start by writing down every single piece of information that they give me. A person invests $3,500. That's the principal. Whatever you started with is the principal. $3,500. In an account that earns 3% annual interest, that's the rate. Change it to decimal form and it's 0.03. Right? 3/100ths. Find when the value of the investment reaches 10,000. So they're telling me what V is. Okay, the final value of V is 10,000. So the question is, what is T? That's what they're asking for. What is T? So what I'm going to do is plug in all of these 3 values into my equation here and solve. So V is 10,000. I'm going to start with 10,000 equals P, which is 3,500, times 1 plus R. 1 plus 0.03 is going to be 1.03 to the power of T. We're going to solve that first by dividing by 3,500 on both sides. So 10,000 divided by 3,500. My calculator says 2.857. Here they cancel, so equals 1.03 to the power of T. Now to solve that is where we need our graphing calculator. So I hope you have your graphing calculator handy. If not, go ahead and get one right now. Pause the video, of course, so you can get one. So there's no way for me to put a graphing calculator here on the screen, but once really quickly I'll explain the steps on how you're supposed to do it. So once you have your graphing calculator, go to the y sub 1, y equals menu, right? Click on y equals, top left corner. And then clear whatever equations happen to be there. And under y sub 1, put 2.857. Under y sub 2, put 1.03 to the power of T. Enter both of those there and graph. Click on graph. And what you should see is a horizontal line. You should see a horizontal line, and you should also see an exponential growth line, something like this. You should see 2 lines that look something like that. And what you care about, as always, is the point where they intersect. So what you need to focus on is on the point of intersection. In order to find it, you need to press on second trace, which is the calculate menu, second trace. Choose option number 5, which finds the point of intersection. And then click on enter 3 times, right? The first time to put it on one of the lines, the second time to put it on the other line, right? It says line 1, line 2. And the third time it says guess, so close to the point of intersection and press enter. And once you do that 3 times, it should give you the value of x, right? Or t, because we're looking for t, but the calculator doesn't know that, it wants x. So it should give you the value of x, which is, according to my calculator here, according to mine, it says t equals 35.52. Let's say 35.5 and leave it like that. And that is your final answer for number 1. So in 35.5 years, the $3,500 account will grow to $10,000. All right, number 2, a person invests $200 in an account that earns 6.25% annual interest. Find when the value of the investment reaches $5,000. So once again, what I'm going to do first is write the equation, my formula for annual interest, which goes V of t equals P times 1 plus R to the power of t. Need to look at my problem and figure out all of the different variables that I have here. It says a person invests $200. That is the principal. How much you start with, how much you invested, that's your principal, 200. 6.25% annual interest, that's R. In decimal form, it already looks like in decimal form, but it's not. It's in percentage form. So you got to turn it into a decimal by moving the decimal over twice. So it's going to be 0.0625. You don't see that, just think. We're moving the decimal 2 times to the left, right? So we need to add another 0 in front of the 6. Okay, next what they gave me is that find when the value of the investment reaches 5,000. That's V. V is 5,000. Plug all of those into your formula. So this is what you should have in your formula. 5,000 equals P, which is 200, times 1 plus R. 1 plus 0.0625 is 1.0625 to the power of t. And that's what we need to solve. Once again, like in the last problem, I'm going to start by dividing by 200. Always do that to make your numbers a little smaller and easier to work with. So on the left side, I have 5,000 divided by 200. That's going to be 25. Right? You can check that with your calculator. But look, cancel the 2 zeros. That's 50 over 2, which is 25. Equals 1.0625 to the power of t. Okay, and at this point is where your graphing calculator kicks in again. Okay, so let me quickly recap the steps. Under y sub 1, enter 25. Y sub 1 equals 25. That's going to be a horizontal line. Under y sub 2, enter 1.0625 to the power of t. Okay, so under y sub 1, enter 25. Under y sub 2, enter 1.0625 to the power of t. And then what you're going to do is you're going to graph that. And then what you're going to do after that is you're going to go to second trace, which is the calculate menu. Second trace, which is the calculate menu. And then once you go into the calculate menu, you're going to choose option number 5, which is to find the point of intersection. Okay. Once you've gone through all of those steps, you should come back with the answer. Your calculator should say something like x equals 53.1 is what mine says here. 53.1. That's the point of intersection of the two lines. So that's t. And that's your final answer. In 53 years, your $200 will grow to $5,000. All right, number 3, a person invests $1,000 in an account that earns 5.5% annual interest. Find when the value of the investment has doubled. I'll let you guys work on that one on your own. So go ahead and pause the video here so you can work on it on your own. Take a couple of minutes and then come back to see the correct answer. Okay, go ahead and pause right now. Okay, so here we go. Number 3, a person invests $1,000 in an account. Here's my answer. I got 12.9 years. So here's how I did it. I put in 20,000 for the final amount because the question is when has the value doubled. If you started with 1,000, double means 2,000, right? P is 1,000, which is the principal, right? The rate is 5.5%, which in decimal form is 0.055. So it's 1.055, right? 1 plus R. The first thing I did is divide it by 1,000 to get rid of that. So I got 2 equals 1.055 to the power of t. And then at this point, I use the calculator, right? Under y sub 1, I put in 2. Under y sub 2, I put in 1.055 to the power of t. And my calculator says that the point of intersection is 12.9. So approximately after 12.9 years, the account will double. All right, let's move on to number 4. A person invests $1,200 in an account that earns 2% annual interest compounded quarterly. Find when the value of the investment reaches $1,500. So the keywords here are compounded quarterly. That means that they're going to compound this amount every in each year 4 times per year, right? Every quarter. Okay. In order to do that, then we need a different formula. We can't use this one. It does not work. Okay. We need to use that second one up there on your notes. Okay. When you compound more than once per year. And it actually, once you understand this one, then you got the other one because it's very simple to come up with it. Okay. It looks very similar. Look. Every time you compound something more than once per year, that's n. That number that you compounded per year, that's n, right? So in this case, compounded quarterly, that's 4. What you want if you're going to compound more than once per year is you want to take your rate, whatever r is, and you want to divide it by the number of years it gets compounded, right? So if the rate is 5%, you need to divide it by 4 because you're compounding it 4 times per year. So you need to divide that up into 4 equal pieces. If your rate is 10, you need to divide it by 4 or whatever your amount is, right? In this case, it's 4, so I'm using 4 as an example. But then you need to also take that n and multiply it times t up here. Because if you're compounding 4 times per year, that means that your total amount, your total number of compounds is going to be whatever t is times that number, right? So in 2 years, it's going to be 8 total compounds, right? And so on. So notice how similar it is to the last formula. You're going to take r and divide it by n, but you're going to take t and multiply it times n. And that is the new formula for something that is compounded more than once per year. You can look back at your notes at that exact same formula. So this is the one we're going to use in this case, not this one. All right, once we have it, it's just a matter of using and plugging in the correct values. It works the exact same way, except now we have a 4 for n here. Okay, so in this case, P is 1200, right? R is 2%, so 0.02. N is 4. So in this case, we need N 4 because it's compounded quarterly, 4 times per year. Punch in those values. Oh, V. V is the total amount at the end. Find when the value of the investment reaches $1,500. So let's punch those in. 1,500 equals 1,200 times 1 plus 0.02 over 4 to the power of nt, 4t. That's a 4. Let me erase that and write it again. This is supposed to say 4t. 4t. There you go. That's what I'm supposed to solve. What I'm going to do first in this case is divide 0.02 by 4, which is 0.005. This is 0.005. So 1 plus 0.005, that's 1.005, right? So that inside the parentheses is 1.005 to the power of 4t. And 1,200 on this side, and 1,500 on this side. So what I'm going to do now is what I usually do is divide by the number in front, which is P. Divide by 1,200. Those cancel. 1,500 divided by 1,200. Look, the zeros cancel. So it's 15 over 12, which is divided by 5 over 4, which is 1.25. I used a little bit of mental math there, but you could do that with the calculator. Equals 1.005 to the power of 4t. Okay, and at this point, calculator again. Calculator comes in. We're going to, under y sub 1, you're going to put y sub 1 equals 1.25. Under y sub 2, you're going to put 1.005 to the power of 4t. And then you're going to find the point of intersection like you always do, right? Graph it. Then go to second trace, which is the calculate menu. Choose option number 5, and that will give you the point of intersection after hitting enter 3 times. So go ahead and do that. I'm going to do that here on my calculator. So my calculator says approximately 11.185. That's what you should have. Now let's round it to 11.2 years. In approximately 11.2 years, the value of the investment will reach $1,500 when it started with $1,200. All right, let's do another similar one. A person invests $600 in an account that earns 6.25% annual interest compounded semi-annually. Find when the value of the investment reaches $1,700. So the same thing, except this one is compounded semi-annually. Semi means half annually, so half a year. So twice per year is what this means, right? Every half year they compound this, so twice per year. So let's write all of our information that we know. They invested 600, that's P. 6.25 annual interest, that's R. But in decimal form, 6.25 is going to be 0.0625. Compounded semi-annually, that's N. Semi-annually, that's half a year, so twice per year. Find when the value of the investment reaches 1,700. That's V. Let's fix that. 1,700. Plug that in into your formula, which I'm going to write again, just to get you guys used to seeing it over and over again. V equals, it's V of t, right? I'm skipping the V of t. V equals P times 1 plus R over N to the power of N t. Okay. By the way, I don't think I mentioned this before, but this is the exact same formula as the first one. They are the same formula. Look, let's compare them real quick. I know I'm going on a little deviation right now, but I want you guys to see that these two formulas are the same thing, the exact same thing, okay? If you only compound once per year, that means N is 1, right? We use this one when you compound once per year, right? Every year you compound. That means N is 1. So if you plug in 1 here and 1 here, doesn't that basically become R over 1, which is just R, and T times 1, which is just T? It's the same formula, except in this one, N equals 1. That's why we don't have to write it there, okay? All right, let's go back to the problem. That was a little deviation just to show you guys that there actually are the same formula. Okay, so now we plug in our values and we solve. V is 1,700. P is 600. R is 0.0625. N is 2. And up here I have 2T. And well, the first thing I'm going to do, just like in the last problem, is divide this, 0.0625 divided by 2, which gives me 0.03125, right? 0.03125. Add 1 to that, so this is actually 1.03125, right? Do that calculation first. You guys can do that on your calculator. To the 2t power. 600 goes here, and 1,700 over here. And as always, I'm going to divide out by 600 to get rid of it here. And same thing on this side. Divide by 600. Which my calculator says it's 2.83, repeating decimal. So 33333 forever. Equals 1.03125 to the power of 2t. And here's where the calculator comes in. Under y sub 1, enter 2.83. Under y sub 2, enter 1.03125 to the power of 2t. Graph them, and then go to the second calculate menu, second trace menu, which is the calculate menu. Choose option number 5 for the point of intersection. You're looking for when these two intersect. And if you do that correctly, your calculator should say, my calculator says 16.92229. Let's round it. Let's leave it at 16.9. T equals 16.9 years. This account, $600 invested, will grow to $1,700 in 16.9 years. I'll let you guys work on number 6, so go ahead and work on this one on your own. Pause the video right here so you can work on it on your own. Take a couple of minutes, then come back to check your answer. Okay, so go ahead and pause right now. Okay, so here's the work and the answer for number 6. The principal is 8,000. The rate is 0.065, right? 6.5%. Compounded daily, that's the key word here. Daily, that means every day. So how many days in a year? 365. That's N. It's compounded 365 times per year. What's the value of when does the value of the investment reach 20,000? So that's V. We plugged in 20,000 for V, 8,000 for P, 0.065 over 365 to the 365 times T power. Then what I did here is I divided this out and I added it to 1, so I got 1.000178. Then I divided by 8,000, so I got 2.5 on the left side, and my equation on this side is just 1.000178 to the power of 365t. And at this point is where I use the calculator, right? Y sub 1 equals 2.5, y sub 2 equals this one right here on the right side. Found the point of intersection to be 14.1. That's your final answer. Right, number 7, a person invests $5,000 in an account that earns 3.5% annual interest compounded continuously. Here's the key word here, continuously. It's not annually, it's not quarterly, semi-annually, daily, not even daily, it's continuously. That means it's being constantly calculated every single second, every single millisecond. They're calculating how much interest it has earned and adding it to the account so they could calculate the interest again and add it to the account and so on. Okay? It's a constant, continuous process. So for that one is where we need our third formula. So go back into your notes in the front page and look for that formula that has a base E. Okay, that's where the base E comes in. When something is compounded continuously, we're going to use this formula right here. V of T, the value of your investment after a certain amount of time, is P, the principal, times E to the power of RT. PERT, it looks like. You can remember it that way, right? Continuously, P, the principal, times E to the power of RT. And R is the exact same thing that we've been talking about. That's the rate. And P is the principal, right? So it's the exact same same terms for each of these variables. They represent the exact same thing still, okay? So let's solve it. It's actually a very simple formula to use. In this case, they tell me that the person invested $5,000, so that's P. So the principal is 5,000. Also, they tell me that the account earns 3.5% annual interest, but it's compounded continuously. But it's still R. That is R right there. R is, in decimal form, 0.035. And they also tell me that when will the investment reach, when will it reach $12,000? That's V. Plug in all of those values and we're going to get 12,000 equals 5,000 times E to the power of 0.035 T. Notice that it's not 1.035. It's just 0.035. It's just R, not 1 plus R. Okay? Make sure you understand that difference between this one and the ones previously, right? When they're compounded annually or compounded more than once per year. So we're going to solve it the exact same way. I'm going to divide by 5,000 here to get rid of that initial number there and make my numbers a little bit easier to work with. It also makes it easier to see in the calculator. When I graph this, I'm more likely to find these two lines if my numbers are smaller. So 12,000 divided by 5,000, that's 12 divided by 5, which according to my calculator is 2.4, right, equals e to the power of 0.035t. And now calculator work. Under y sub 1, enter 2.4. Under y sub 2, enter this, e to the power of 0.035t. And then find the point of intersection, the same method, right? Second calculate, second trace, which is the calculate menu. Option 5, intersect. Press enter 3 times. And remember, when you're doing this, I just got to mention again, make sure you can see the intersection of the two lines, right? There's a horizontal line and there is a exponential growth line. Make sure you can see the point of intersection. If you can't see it, then you need to adjust your window so that you can see it. Okay, move the window to the right, to the left, up, down, whatever you need in order to be able to see the point of intersection, and then you'll be able to find it, or else your calculator cannot find it. Okay, so once you do everything here correctly, you're going to get, according to my calculator here, my calculator says 25.013, so approximately, let's just leave it at 25 years. It's close enough. 25.01 something something something. In approximately 25 years, the $5,000 that were invested, compounded continuously, have grown to $12,000. They more than double. Let's compare that to number 6 actually. Let's go back. This is a very interesting point here. Look back at number 6. We invested in number 6 $8,000 and we did double it, right? More than double. It went all the way up to $20,000. The rate was much better, 6.5 compared to 3.5. That's a lot better. That's twice, more than almost twice as much. But this one was compounded daily, and this is compounded continuously. However, they both grew about the same amount, right? They more than doubled. 5,000 became 12,000. 8,000 became 20,000. They grew by a lot. But this one had a smaller rate. What's the difference? The compounded continuously. When you compound something continuously, it's constantly being calculated and added to the investment so that you could find a new number. Okay, I'll let you guys work on number 9 on your own, right? Go ahead and work on that one on your own. As always, pause the video right now, do the problem on your own, take a couple of minutes to figure it out, and then come back and see if you got the correct answer. Okay, so go ahead and pause the video right now and come back to check your answer. Okay, here you go. This is the correct solution, answer to number 9. Let me just really quick guide you through it. 2,000 is the investment that we want, right? We wanted to reach 2,000. 1,550 is what the principal was. 0.04 right here is R because it comes from the 4% annual interest. So 0.04T. And the base is always E for anything that is compounded continuously, right? This is the key word here. That's how we know we're supposed to use E as our base. I divided by 1,550 here on both sides to get approximately 1.29 on this side. It's like 1.2901 something something something. I rounded it to 1.29. E to the 0.04t, and then I use the calculator once again. On y sub 1, 1.29. On y sub 2, e to the power of 0.04t. And then after I did graph those, I found the point of intersection, and the calculator tells me that it's 6.4 years. Which means that in approximately 6.4 years, the 1,550 that was deposited into this account will grow to $2,000. All right, let's move on to number 10. Arturo plans to make a deposit in one of the accounts shown in the table. Which account should he choose? So account X has a nominal annual interest rate of 2.5%. Nominal means by name. That's what it says on the brochure, right? It says 2.5% annual interest rate. it's not really 2.5%, right? All of these really depend on how often they're compounded, right? This one's compounded quarterly, this was compounded monthly, so that makes a difference into how much you're going to make. The other one is 2.48%. So at first glance, this one looks better, right? 2.5%, that's a much better growth than 2.48%. It's a little bit bigger. The compounding period, though, for this one is quarterly, so only 4 times per year, where this one is compounded monthly, 12 times per year. Okay, so that might be the difference right there. So what we're going to use to solve this problem is, let's go back to the first page of your notes, the last thing in your notes that we did that mention. So let's go back a little bit. Let me zoom in up here. What we call the nominal interest rate versus the effective interest rate. Okay, nominal interest rate is R. It's basically what it says on the paper. Whatever they tell you, that's the nominal interest rate. By name, it's 3% or 4% or 5%, whatever they tell you it is. But it's not actually the actual interest rate. That's what we call the effective interest rate. The effective interest rate is the actual interest rate that the account earns annually, right? And it changes based on how often it's compounded, right? The more times it's compounded per year, the better it is, the more it's going to grow. So in order to compare them, we've come up with these formulas. There's 2 of them here, and I'm going to underline them both. For calculating the effective interest rate, so we could compare 2 different accounts, okay? So the first one is for accounts that are compounded more than once per year, or once per year as well, right? They work for once per year as well. It's this formula right here, okay? And if you notice, it's basically the same thing. Look up here. It's the same thing as this, right? 1 plus r over n to the power of n times t, except no p, right? We don't need the principal. We're just comparing the rates. That's all we're doing here. So we don't need to know what the principal is. We're comparing the rates. Also, no t, because it doesn't matter how long we're going to keep this account. We're just comparing the rates, okay? So notice that it's the same thing as this, without the t, without the p, but then subtracting 1, okay? And the reason we subtract that 1 is because we're subtracting the 100%, right? Just like when you add 1 plus something, then what we do is we subtract it to see what the actual rate is, okay? That is for accounts that are compounded either annually or more than once per year. That's for those 2. For accounts that are compounded continuously, we calculate it in this form. And notice that it's basically the same thing. No t, no p, right? It's just e to the r, and then again subtract 1 in order to calculate the actual effective, what we call the effective interest rate. And that way we can compare 2 different rates to see which one is better, okay, by calculating the effective interest rate. So let's go back to that problem. So what I'm going to do here is I'm going to do 2 calculations. So I'm going to split up my work here. I'm going to call the first one rate X and the other one rate Y. So I could calculate their effective interest rate. So for rate X, remember it's the same thing as an interest rate compounded more than once per year, except no P, right? So forget about the P. It's just 1 plus R over N to the power of N. No T, no P, no T, and then minus 1. Same thing over here. And you know what, to make it a little clearer for you guys, I'm going to do it in a different color so you see the difference between the 2. Here's Y. And then 1 plus R over N to the power of N minus 1. We're going to calculate that for both of them to see which one's better. Okay, so let's go ahead and do the one on the left. For account X, it's going to be 1 plus R, in this case is 2.5. So again, in decimal form, always 0.025 over N. Okay, N is the number of times it gets compounded per year. Quarterly, that means 4. To the power of N minus 1. Whoops. To the power of 4, right? Let's go ahead and put that in there. To the power of 4 minus 1. And we're going to do that calculation with a calculator to make our life easier. So 0.025 divided by 4 is the first thing I'm going to do, which is 0.00625 according to my calculator. So this is going to be 1.00625 to the power of 4, because that's n, minus 1. So I'm going to do that last part. 1.00625 to the power of 4 is 1.0252 25235. Let's leave it as 4. Minus 1. So 1.02524 minus 1 is 0.02524. Which, in order to compare, I'm going to change it back to percent. So it's 2.524%. That's the one on the left. That's account X. Let's do the same thing for account Y. Watch. R sub Y, account Y, is 1 plus R, in this case, is 2.48. So it's 0.0248. This one is compounded monthly. That means every single month, 12 times per year. N is 12 in this case. And again, N is 12 up here, minus 1. Right? Remember, it's the same formula as the interest compounded more than once per year, except no P, no T. Right? And then you have to include a minus 1 there at the end. So let's do the calculation here. Once again, just use your calculators to figure all this out. It's actually just calculator work at this point. So I went ahead and did the next part already. It's going to be 1.002067 to the power of 12 minus 1. And then I'm going to do that one, raise it to the 12th power. I get 1.025. 25087, 088 actually, minus 1, which is 0.025088. Change it back to percent form, and it's 2.5088. 09. Let's leave it to 3 decimal places, just like the one on the left. 2.509%. So which one is better in this case? It looks like the one on the left. Account X is better. 2.5% ends up being better than 2.48%. It's compounded quarterly, which doesn't sound like too much. Well, this one is compounded monthly, but still, this little bit of edge on the percent rate ended up beating out the other one. So if I was Arturo, I would choose account X. Alright, let's do another one. Harriet plans to make a deposit in one of two accounts. Account A has a 3.25% nominal rate. Account with interest compounded continuously. So this was compounded continuously at 3.24%. Account B has a 3.25% nominal rate. Interest compounded semi-annually. Okay, so they have different rates, and also they're compounded differently. Okay, now notice how close the percent rates are, 3.24% to 3.25%. They're very, very close. So just by looking at that, you would say, I choose that one. That's better than that one, right? 3.25% is better than 3.24%, right? But the difference is how often they're compounded. This one's compounded continuously. This one twice per year. So let's see the difference. I'm going to put account A on the left side. So we're going to call it rate A equals 1 plus R over N to the power of N minus 1. That's the formula. So let's plug in the values. R sub A equals 1 plus R, in this case, in account A, is 3.24%. Change that to decimal, and it's 0.0324 over N compounded continuously. Ooh, I just messed up. I just noticed that. Continuously, not more than once per year. Let's erase everything I just did. If you caught it before that, good job. I'm just testing you, of course. Let's go back and actually put in the correct equation, right? For compounded continuously, here it is. we're still going to call it R sub A, is going to be e to the R minus 1, which is actually the easier one of all, right? Compounded continuously. So in this case, all we care about is what is R. R in this case is 3.24%, so it's going to be e to the 0.0324 minus 1. Punch that into the calculator. My calculator says 1.03293 minus 1. So it's 0.039, nope, 293. In percent, it's 3.293%. That's account A. Let's do the same thing now for account B. Now, before I put in the wrong formula, let me reread it again. It says it's 3.25% compounded semi-annually. Okay, so as long as it's not continuously, we don't need to use this one. That's only for continuously. Semi-annually, we're going to use that other one that I was trying to use before. Okay, so semi-annually, that means that my rate is going to be 1 plus R over N to the power of N minus 1. Plug in R, which in this case is 3.25%. So 1 plus 0.0325 over N semi-annually. That means twice per year. N is 2. To the power of 2 minus 1. At this point, it's calculator work. According to my calculator, this becomes 1.01625 to the power of 2 minus 1. And then you square it, and it becomes 1.032764 minus 1, which is 0.03274, which in percent form is 3.276. Let's leave it to 3 decimal places just like the other one, percent. So which one's better? You compare those two numbers, the one on the left is definitely better, right? So this, even though the rate is smaller, it's not that much smaller, but because it's compounded continuously, it ends up being a much better rate than this one over here. Okay, so let's again explain the difference. This is the nominal rate. This is what they tell you the rate is. This is the effective rate. This is what it actually earns per year, right? Because it's compounded continuously. In account B, this is the nominal rate. This is what they tell you. Oh, it's 3.25%. This is the effective rate. This is what it actually earns per year because it's compounded semi-annually. Okay, so know the difference between the two. Nominal rate, effective rate. Nominal rate, effective rate. The nominal rates, this one's better. But really, this one's better. Account A is better because the effective rate is much higher. Okay, your turn, number 12, the last one in this section. Jacqueline plans to make a deposit into one of the two accounts. Which account should she choose? Go ahead and do what I just did using the formulas that I just used. Notice what it says. Compounded annually, that means once per year. Compounded daily, that means 365 times per year. Okay, so go ahead and do that comparison and see which one she should choose. Go ahead and pause the video right now. Work on it on your own for a little while, then come back and check your answer. Right, so here's the answer. For account X, it's compounded annually. So this is actually something very important to see. If the account is compounded annually, after my calculations, that means N equals 1, once per year. So it really is just 1 plus R minus 1, which ends up being that your answer is R. Your nominal interest rate, 4.24%, is the same as your effective interest rate, 4.24%, because it's only compounded once per year. So it's actually the exact same thing. Account Y is compounded daily, which is 365 times per year. So I plug in 365 for N. R is 0.0418. That's what I put here because it's 4.18%. Notice how huge of a difference there is between the two accounts. Okay, doesn't seem like a lot probably to you guys, but this is a big difference from 4.24 to 4.18. I did the calculation here. It ended up being 1.000111452. I left it to as many decimal places as I could so that when I raised it to the 365 power, I got as close to the actual answer as I could get. I got 1.04268. Subtract 1, it's 0.04268. And turn it into percentage form, and it's 4.268. And I compare the two, and this one ends up being much better than that one, right? It's 0.02% better. 4.26 to 4.24, 4.27 actually if we round it over to another decimal place. 4.27 to 4.24, that's 0.03% better than the other one. Even though it started out being worse, it actually is better because it's compounded daily, which is a big difference. You compound it 365 times per year as opposed to you compound it only once per year. Okay. And that concludes, that's the last problem on the section. Hopefully you guys understood every single problem. If not, you can always go back and re-watch it. Okay, from this point on, you're on your own for the homework.